Here we go. This is the next section. This one's all about friction. You've probably heard the word friction, but let's dive into how to actually mathematically solve for this. So what are the purposes? We've got understanding the concept of friction and then exploring the difference between static and kinetic, because there's actually two different kinds of friction that we're going to deal with today. And then we're going to solve some questions. So what is friction? Well, friction is created whenever you've got two surfaces that move past one another. So if you take your hands, you rub them together, you're going to generate some heat, and that's due to friction. So if we were to look really, really closely at two objects as they're moving past each other, you've got this. So here's a picture of a crate moving along the ground. You can see that there's these bumps and ridges, and those catch on each other as you're moving along. You can imagine your fingerprints. There's a bunch of bumps and ridges on your fingertips. Those actually cause you to grip something well because it creates a greater amount of friction. There's more bumps and ridges, and it's more pronounced on your fingers. So if your hands are wet, water gets into those ridges, and then your hands become less sticky, or it becomes harder for there to be friction because those ridges are filled by water. So we have an equation for friction. It's given by this. So force of friction equals mu times Fn. So Fn is the normal force. Now the normal force is the force that is caused by surface. You've seen this in the last unit, and it is always going to be perpendicular to the surface. So if this is my surface, the normal force always points straight up from that. And I'll give you a teaser for the last section in this unit. We're going to take surfaces that are flat like this, and we're going to rotate it, and your normal force rotates with it. So we're going to get to that later, just so that you know it's coming. So I said that already. Normal force is perpendicular to the surface. Mu is the coefficient of friction. So there's no unit for this. It basically tells you how sticky something is. The bigger the mu, the more amount of friction you're going to have. This is a Greek letter mu. You're going to notice lots of Greek letters showing up. And mu depends on both surfaces. Somewhere out there, I haven't seen it, but it's a rather boring textbook that has a list of a whole bunch of different coefficient of frictions. So they try a bunch of things. So they're like, okay, what's the coefficient between ice and this type of wood? And what's the between ice, and between ice and rubber, and between ice and plastic, and between ice? So somebody out there has gone through and made this whole bunch of stuff, done a bunch of experiments, but it depends on two surfaces, not just one. So we have two different types of friction. One of them is static friction. So static is on a object that is stationary, not moving. And we've got kinetic friction. So kinetic friction is friction on a moving object. The static friction is bigger than the kinetic friction. That's always going to be the case. And therefore your mu s, or the coefficient of friction on a static object, is going to be bigger than the same two objects when they're moving. So that's always going to be the case. You can check on your formula sheet and compare between the static and kinetics, and you can see that that is actually true. So let's do an example here. We've got a box of donuts pushed along the floor with 42 newtons being applied. The coefficient of friction is 0.443, and we want to know what is the force of friction. So let's take a look at our free body diagram and see what's going on. So here's a box of donuts. We've got force of gravity down, normal force up. Those two are going to be equal because we're not accelerating up or down. We've got a applied force, and we've got force of friction. And we aren't told if we're accelerating or not, but we're going to assume that because it would have to tell you it's moving at constant velocity for these two forces to be balanced. So force of friction is mu Fn. In this case, Fn is equal to Fg, and since we're not floating around in the middle of space, we're on the surface of the planet, Fg is just going to equal mg. Those numbers we all know, plug those into your calculator, you get the force of friction is 25.6 newtons. The same situation, we're going to solve for acceleration. There's a cat that just walked past my window. So F net is equal to the bigger force minus the smaller force, so force applied minus force of friction. We know F net is equal to m times a. We've already solved for force of friction. So force applied is 42. Force of friction was from part A. We know the mass. Solve for acceleration. We get this. Let's do another one. So we've got an object pushed along the ground with a different force. So different force applied. If it moves at a constant velocity, what's the coefficient of friction? So let's look at our free body diagram again, just so we can get comfortable with what's going on. Force of gravity. normal force, those are balanced because we're not accelerating up or down. We have a force applied and a force of friction, but in this case, these two are also equal to each other. Again, double lines because they are not the same as the normal and FG, so I can't do them all as a single line. So what does our equation look like? Well, since all my forces are balanced, the applied force must equal force of friction. We have an equation for force of friction. We know Fn is equal to Fg, so I just plugged in already mass times 9.8, and then we get that mu is 0.768. Another example here, we want to know what's the minimum amount of force required to start moving a 1.2 kilogram water bottle if we've got a static coefficient of friction and we've got kinetic. So in this case, if we're trying to get this object started moving, it is at rest. It is not moving yet. We want it to get it moving. So that means we're going to look at our static. So we've got the same free body diagram. We're just trying to get it started. And force of friction, we're going to use this static coefficient of friction because we're starting to move the object. Here's the equation, plug in the numbers. Force applied is 2.47 newtons. So if we do the same question, or same situation, except now what's the force to continue moving the water bottle at the constant velocity? Meaning, we've already started to get it moving. Now, what's the force required to keep it moving? Same free body diagram. We're dealing with the same equation because it's constant velocity, except now we're using the kinetic coefficient of friction. So we have that, plug in our numbers. So notice the force applied is smaller, which makes sense because it's harder to get an object started moving than it is to keep the object moving at a constant speed. And remember, with Newton's law, an object wants to stay at rest or it wants to move at a constant speed. So it's harder to go from at rest to some velocity than it is to maintain constant velocity. That's just Newton's first law. So there you go, that's friction. You're gonna have to use a lot of F-net equations like we learned back in Newton's law unit. So get comfortable with that because you're gonna use that quite a bit with force of friction. All right, Girly, do you think everyone's figured out who you are yet?
Maybe.
Maybe. Maybe. They'll probably ask me in class.
Okay.
Okay, sounds good. All right, so this clip is from a movie called Ratatouille, and this one's about a rat who likes to cook. Is that silly?
Yeah.
Okay, watch this one and see if you think this is possible. This one's a little bit more biology than physics, but we're going to include it anyways. Okay, you ready?
Yes.
What do you think?
I don't think that his hair can make him move.
Do you think that your muscles in your arms are connected to your hair?
No.
No. So if he does something like this here, you don't think he can make him lift his arms with lifting his hair? Shall we try it? Wait, I'm gonna lift your hair. It's not working. Shouldn't your arms be moving if I wiggle your hair?
No.
No, that's not how it works.
Yeah.
That'd be rather silly, wouldn't it?
Yeah.
What if your classmates came and started playing with your hair? What would happen?
Nothing.
Nothing. But if it was like in the movie, what would happen? When I've lifted your hair like this, then your arms would start wiggling.
Yeah.
That'd be so silly, wouldn't it?
Yeah.
Okay, that one's kind of an easy one.